And welcome back. So last time we went through some dynamic optimization. We talked about the Euler equation, what it meant in both sort of like a macroeconomic framework or context, also a couple of ways that we could try to use it in sort of everyday life, like how we do our individual planning, our consumption savings patterns, plannings over time, things like that. But I know just chugging through a lot of mathematics isn't always the best way to really drive this point home, so to speak. So what we're going to be doing now is looking at a graphical representation of dynamic macro, namely what this will look like if we were to use indifference curve analysis, like from intermediate macro. So yeah, let's just go ahead and get started with it. So what we're going to want to do is begin with a budget constraint. We'll go ahead and erase this since we already know what chapter this is. Again, if you hear any noise outside, if you hear like hammering or if you hear a saw going, anything like that, they're doing construction on the outside of my apartment. There is really very little that I can do about that. I have absolutely no idea how I'd even try to begin to edit that out of this video, so bear with me. I'm doing the best I can. I have absolutely no control over that. So what we're going to want to do with this budget constraint is look at it in a visual form rather than just a mathematical form. The mathematical form, right, was just that intertemporal budget constraint, but we can look at it graphically. So we're going to make a graph. With current consumption on the horizontal axis and future consumption on the vertical axis. And we're going to have a budget line which is going to be describing the intertemporal budget constraint that the economic agent faces. Actually, I will write out the budget constraint first. So if you recall, we could express the budget constraint a number of ways. Right? We could have like this right here. Right? And this budget constraint, what this thing actually does is it's going to give us all possible combinations of current and future consumption that max out our constraint. Now, if we were to plot this guy out, right, what we would get is the following. We would get this right here. So when we plot this out, we have some point, we'll put it right here just for ease. Because if you look at this constraint here, you'll see it's It's got CT plus 1 and CT, but it also has YT and YT plus 1. All right, well, the budget constraint is going to depend on that. And it's also going to depend on the interest rate, which we'll be talking about in a moment. Now, at this point here, we have what's known as the endowment point. And I'm making every attempt to use the same color coding in this lecture that I have in the book. So this is our endowment point. All right, at this endowment point, it is a point on this budget line, all right, because this right here, graphed out, is this pink line here. This endowment point is a point on that budget constraint, or that budget line, where we've got YT, current income, and YT plus 1, future income. So at this endowment point, so at this endowment point, we can describe what's going on with the placement of current and future income. So the intercepts, the CT plus 1 intercept and the CT intercept, what are those? And also, what would they mean? How would we want to interpret these things? Well, let's look at this constraint and see if we can't get a little bit of understanding from it. All right, so what are these intercepts going to be? Well, if we look at the CT intercept, right, or if we think about this in like XY space, it would be the x-intercept. All right, intuitively, what does that tell us? What's going on at this point right here where the budget line crosses the CT axis? Well, what that tells me is the CT intercept CT plus 1 equals 0. And that tells me the agent consumes everything today and nothing tomorrow. All right, so that's like if we're looking at this just over, say, 2 days. You get paid today, you get paid tomorrow. And you know what you're going to get paid today. You get paid YT. You know you're going to get paid YT plus 1 tomorrow. Now, these two can be the same. They can be different, right? You could get paid more tomorrow than you're getting paid today. You could be paid less tomorrow than you're being paid today. But this is a deterministic system, right? So there's no uncertainty. There's no uncertainty about what future income is going to be. We know what it's going to be. So it's another simplifying assumption. If we wanted to add uncertainty into this, things get a little weird, and that's more like graduate level, like macro work, because we can really squeeze a lot of information out of just a deterministic system. But if I know what my income is going to be both today and tomorrow, let's say I make $100 today, I'll make $100 tomorrow, right? Well, I'm going to have my lifetime income, right, would be that $100 today plus 1 over 1 plus the interest rate times my income tomorrow. So if I wanted to spend all of that, right, I would be borrowing from my future self to consume everything today, and then tomorrow when that income, well, comes in, every single bit of income I get, I have to repay that debt that I had accumulated the day before. So I consume everything today, and then tomorrow all I'm doing is just paying off everything I consumed today. So it would be the equivalent of like maxing out your credit card today and paying it all back tomorrow, but you don't get to consume anything tomorrow because, well, you have to pay back your debt. You got to get a zero balance on that credit card again, right? So if that's the case, CT plus 1 equals 0, so we would have 0 equals 1 plus the interest rate times YT minus CT plus YT plus 1. Right, so 1 plus the interest rate times YT minus CT. What is YT minus CT? Well, if we remember the resource constraint, YT minus CT was investment. It was savings, right? Whatever you don't consume, you save. So of your income today, if whatever part of that income you consume, if you subtract what you consume from what you make, that's what you save that gets put forward tomorrow. All right, in this case, we actually have negative savings. But let's go ahead and solve this thing out. All right, we're going to want to solve this for CT. Why do we want to solve it for CT? Well, because that's the axis that we're interested in. So we want this in terms of CT when CT plus 1 is equal to 0. So what do we do? Well, let's see. Let's go ahead and distribute this 1 plus r all the way through this YT minus CT. So I have 0 equals 1 plus RT times YT minus 1 plus RT times CT plus YT plus 1. All right, well, if I add that 1 plus r times CT to both sides of the equation, I get 1 plus r times CT equals 1 plus r times YT plus YT plus 1. Now I want to divide both sides by 1 plus r. Like that. And I find CT equals YT, because 1 plus r divided by 1 plus r is just 1. So it's YT plus 1 over 1 plus RT. Another way we could write this, of course, is CT equals YT plus 1 plus RT to the power of negative 1 times YT plus 1. Either of these will work, well, because they're the same. I understand what it is. Whichever one you prefer to use is whichever one you are allowed to use. So here I have, oh, excuse me. That burp was brought to you by I have absolutely no idea. So at this point, I'll just have YT plus 1 over 1 plus RT. Like that. All right, so what this says is my consumption, if consumption tomorrow is 0 and I consume everything today, this is how much I can actually consume, right? YT is my income today, YT plus 1 is my income tomorrow, but I have to discount my income tomorrow by 1 plus the interest rate, right? It's discounted present value, if you remember that from principles of macroeconomics. So I've got to discount the present value of my future income, which means I'm not actually consuming all of my future income because it's being discounted by some interest rate. Why? Well, think about it this way. If you got to pay it back later, that interest rate is going to come into play. And you're going to have to pay it back plus interest. Boom. So that's the CT intercept. Right? The CT plus 1 intercept is what happens when we consume absolutely nothing today and absolutely everything tomorrow. So we consume absolutely nothing today and everything tomorrow. How do we do that mathematically? Well, if we consume nothing today, CT is equal to 0. So I just plug CT equals 0 in to this budget constraint, and I get CT plus 1 equals 1 plus the interest rate times YT minus 0 plus YT plus 1. I can simplify that because YT minus 0 is just YT. So I get CT plus 1 equals 1 plus the interest rate times YT plus YT plus 1. So what does this mean? Well, it means I save absolutely everything of my income. All of my income gets saved in the first period. So I spend absolutely nothing. So because CT is equal to 0, then investment or savings, because the two are equal, IT or ST, is equal to YT. So income equals savings. I literally save everything. So if I save everything, I consume nothing, what I get to consume tomorrow is 1 plus the interest rate times however much I saved. Right, so if, let's say, YT were 100, YT plus 1 is 100, interest rate 0.05 or 5%, right, what I get is CT plus 1 equals 1 plus the interest rate, so it's 1 plus 0.05 times 100 plus 100, because I'm saving that $100 of the first period income, which means tomorrow what I get back is that income, the principal, what I saved, plus 5% of that. So CT plus 1 equals 105 plus 100 equals 205. So if this is dollars, then my future consumption, if I consume everything tomorrow and nothing today, my future consumption is $205. So let's go ahead and label this CT plus 1 intercept right here. 1 plus RT times YT plus YT plus 1. Kind of didn't have a lot of space there. All right, now let's look just for a second at what our consumption would be if, again, this held. So I've got YT is 100, YT plus 1 is 100, the interest rate is 5%. Let's look at what consumption would be if I consumed everything today and absolutely nothing tomorrow. How much would consumption be? Well, let's take a look. So CT is equal to this. Right, so YT is 100. YT plus 1 is also 100. Interest rate 0.05. So it means CT is equal to 100 because I consume everything I earn today, but I got to borrow from my future income. I got to borrow from tomorrow's income. And if I do that, well, I can't just take all of it because I don't have it. So if I borrow it from somebody and I got to pay it back, they're going to go, okay, well, what's your income tomorrow worth to you today? Right? So if you ever, hear about like those settlements, somebody wins the lottery, like what JG Wensler, I think, something like that. Like, it's my money and I want it now. Well, when you win the lottery, if you want a lump sum payment of that lottery, right, because when you win the lottery, they just kind of give you a bunch of money over a really long time. Or you can opt to get a lump sum payment. If you want that lump sum payment, you don't get anywhere near as much as if you had just waited it out and taken the full stream of, I guess, new income, or the income boost. So when you win the lottery, if you just want it all now, well, it would be like, if it paid over 2 periods, yt plus 1 over 1 plus rt. So I will add in 100 divided by 1 plus 0.05. So CT is equal to 100 plus 100 over 1.05. And I move over to my handy dandy calculator, which is attached to my phone. Give me one moment. Let's see, okay, here's my calculator. Well, what that gives me is CT equals Yes. $195.24 is what I can consume today if I consume everything today and absolutely nothing tomorrow. Right, so by borrowing from myself, I end up not being able to consume as much as my lifetime earnings because I want it all now, right? I'm being impatient. Now, just to clarify, this is only looking at the budget constraint. This is not looking at individual preferences, right? So the beta equals 1 over 1 plus rho, that discount factor, where rho is a discount rate, isn't showing up in this, right? I am just making a couple of wild assumptions about what our time preferences could be. So, now that that's out of the way, right? Because we haven't done anything with the utility function yet. With that out of the way, and we have our intercepts, we can press forward a little bit. So what's the slope of the budget line? How do we figure out what the slope of the budget line is? Well, let's, maybe I effed up a little bit by erasing the budget constraint. All right, well, if this is my budget constraint, my budget line, and I want to know the slope of it, what is the slope of any line? Well, it's the change in y over change in x, if we're looking at xy space. Right, rise over run. Well, if I want rise over run, in this case, if I want delta y over delta x, I want the change, or y, remember, is the vertical axis, in, what's my vertical axis here? Well, it's ct plus 1. So I want my change in ct plus 1 over my change, the run, right? The change in ct plus 1 is the rise. Now I want the change in the run. Well, change in that is ct. So it's the change in ct plus 1 over the change in ct. We think we have any idea where this is going? Well, if you thought calculus, then you are 100% correct. There is my eraser. Well, what I get is the derivative of ct plus 1 with respect to ct. So what this tells me, I take the derivative of this guy with respect to ct. So everywhere I see a ct, well, okay, cool, that's what I take the derivative with respect to. All right, well, what is that going to give me? Well, I got this 1 plus rt times yt minus 1 plus rt times ct plus yt plus 1. Well, this yt and this yt plus 1, actually, before I take this derivative, let me expand it out a little bit so it's easier to see what I'm doing with the derivative. Now, this is a much easier way of looking at it when we want to differentiate it. So ct plus 1 equals 1 plus r times yt minus 1 plus r times ct plus yt plus 1. And I want the derivative of ct plus 1 with respect to ct. 1 plus rt times yt goes to 0. There's no ct there. Negative 1 plus rt times ct, there's a ct there. So what's the derivative of this with respect to ct? Well, negative 1 plus rt. And then this yt plus 1 differentiates to 0. There's nothing there. Which means the slope of this budget constraint negative 1 plus the interest rate. All right, why is it negative 1 plus the interest rate? Well, there is a trade-off between current and future consumption. If I want more consumption today, I've got to give up more consumption tomorrow. So it's negative because of trade-offs between current and future consumption. If I want more consumption today, to give up some future consumption, which means ct plus 1 will fall. Right, and you can plug numbers in here and see exactly what's going to happen. Right? If you want to pick a point here and a point here, you'll see that, well, the slope of this has to be negative because we face trade-offs. So because of these trade-offs, we get a negative budget line, which is interesting. And it tells us, well, okay, cool. If I want to consume more tomorrow, that means I can't consume as much today. I have to save today in order to be able to consume more tomorrow. Resources are finite. We don't have an infinite number of resources, so if we want to consume more today, we have to give up some consumption tomorrow. Because if you take out any debt, the best way to really think about it is you're not borrowing from somebody else, you're borrowing from yourself. Somebody else is facilitating that, I guess, exchange between current you and future you. Right? Like How I Met Your Mother with future Marshall and future Ted when they're thinking about going out and getting drunk. They're like, well, we'll be pretty screwed tomorrow. And then, I don't remember whether it's Ted or Marshall, one of them goes, you know what, that's a problem for future Ted and future Marshall. And then the other one, whether it was Ted or Marshall, I don't remember, goes, yeah, let those poor slobs deal with it. Right? If you go out drinking and you want to go out and get hammered one night, well, you're going to be really hungover and super miserable the next day. And when you're super miserable next day, the way you can sort of think about what happened is, the night before, you went out, you partied, you got really drunk. A lot of people like getting really drunk. You get really happy when you get really drunk. But you're borrowing that happiness from tomorrow. So you're going to be super, super duper, super double duper happy tonight. But then tomorrow morning rolls around and you're not really very happy. You borrowed happiness from tomorrow to have more happiness right now. That's kind of what the budget line's telling us. Right? You can sort of think of this budget line as alcohol consumption. Holy shit, I'm getting fired. Anyways, so if that's what the budget constraint is telling us, let's just go a little bit further with this. Because we figured out where the budget line is going to cross the CT and CT plus 1 axis. We figured out what the slope of the budget line was. Right, so the slope told us the rate of change of it, and then the intercepts told us the placement of it. Because we need both in order to be able to figure out what this line is going to be telling us. Right? So, when we think about what happens with this interest rate, a higher interest rate will induce you to save more today. Right? It induces you to save more today, so you can consume a lot more tomorrow. But remember, this budget constraint doesn't have any information about utility. So I'm going to ask, how much is it going to induce you to save? Right? If the interest rate goes up by 1%, how much more are we going to save? Well, the budget line doesn't tell us that. What does tell us that is the utility function. So we need a utility function to tell us what that's going to be. So if you remember, utility, lifetime utility. Now I'm just going to do this in an abstract utility, like functional form. I'm not going to do log utility because it just honestly doesn't particularly matter. We'll have utility of consumption today plus beta times the utility of consumption tomorrow. All right, that's our utility function. And if we remember from the dynamic optimization stuff, I'll say at the optimal consumption savings point, we have the Euler equation. Now the Euler equation, if we had log utility, if you remember, it was 1 over Ct equals beta times 1 plus r times 1 over Ct plus 1. What that told me was marginal utility of consumption today equals beta times 1 plus the interest rate times the marginal utility of consumption tomorrow. U prime of Ct is marginal utility today, or marginal utility of consumption today. U prime of Ct plus 1 is the marginal utility of consumption tomorrow. So let's get into a little bit more with this utility function. Don't worry about me erasing this stuff, we will be coming right back to it. Section 8.3, utility function. Again, remember utility in the 2-period model is U of Ct plus beta U of Ct plus 1. Right, well, if I've got utility of consumption today and utility of consumption tomorrow, all right, that tells me that, again, yay, trade-offs, right? My preferences over time will determine the marginal rate of substitution between current and future consumption. What does that give me? Well, it tells me I can get indifference curves for the agent's preferences between current and future consumption. All right, so let's draw another graph. So I have, again, current and future consumption. All right, so it's the same set of axes that we had for the budget constraint. And we're going to have some curve, an indifference curve, that describes the agent's preferences at any point for current or future consumption. Right, along this particular indifference curve. So let's say I draw one indifference curve. What color do I use? A nice My Adrian monk coming through. So let's draw this particular indifference curve, and let's label it u sub 0. Right? At u0, actually, you know what I'll do? I'll erase this and redraw it with a better marker. It's a little bit more visible. Ah, yes, much nicer. So at u0, this is a particular level of utility. Right? So if we can put utility, describe it on some metric, we can have this level of utility that is like, say, 100. Right? So that's like going, I am happy at a utility level of 100. I have, God, I hate this word, like 100 joules of utility. Now, if I want to consume this much tomorrow and this much today, it is on this particular indifference curve, and I am happy. I'm at a level u sub 0 of utility. If I wanted to consume a little bit more today, call this CT prime, well, I would have to consume a little bit less tomorrow, CT plus 1 prime. I'd have to consume a little bit less tomorrow if I want to consume more today, and still remain on this level of utility. Right, so let's call we'll call it CT plus 1, bundle 1. And I guess we're going to call it something. We're going to give it a name. May as well capitalize it. All right, that would be a proper noun. It would be improper to use lower cases on a proper noun. And we'll call CT prime CT plus 1 prime bundle 2. Right, well, at bundle 1 or bundle 2, I'm at the same level of utility. I'm at the same level of happiness. So they're at the same level of utility. And thus the agent is indifferent between the two choices. The agent just does not care. Whether he's at bundle 1 or bundle 2, he is just as happy. So if he or she are just as happy at bundle 1 or bundle 2, well, they're on the same level of utility. They're indifferent between that, and if they wanted to choose a consumption bundle here, 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 anywhere on this continuum of points on this particular level of utility, they are indifferent. They literally do not care. But this is just one indifference curve. Let's add another indifference curve. First, I'm going to erase this stuff here. Don't feel like you have to draw a new graph or anything like that. You can double this up on your notes. However you take notes is none of my business and all of your business anyways. All right, so this is one level of utility. Well, what will another level of utility give me? see what color we have. I like a light blue. So I'm trying to, again, keep the colors consistent with what I have in your book. Yeah, shoot. Let's call this U1. Well, this is a different level of utility. Why is there a different level of utility? Well, we have different levels of utility for a reason. I mean, we obviously have to have some kind of a reason for why we would have different levels of utility. Different levels of utility exist for different levels of income. So at U1, I'm making more money. I'm earning more income. You can call it like a higher standard of living. Then at U0. Right, so if I make more money, I really don't need to say make more money because we haven't introduced money into any of these models yet. If I'm earning more income, then my level of utility will increase. So if I want to draw another one, oh, I can also do that. Call it U2. Not after the rock band that was absolutely phenomenal up until like 1989, and then just kind of went downhill after that. No, after just the next level of utility. So at U2, I have a higher income than I do at U1, which is a higher income than what I have at U0. Right, so we would like to be at as high as possible a level of utility. But what's constraining this level of utility is our income, our budget constraint. Right, the budget constraint is going to be determining which of these levels of utility I am at. So let's answer one other thing really quickly. Let's see, do I want to talk about this or do I not? I don't think I want to talk too much about it. I think what I would rather talk about is just that in order to hold utility constant, right, so at one particular level of utility, at any particular level of utility, I want more of one input, so CT plus 1. Let's say if I want more of CT, if I want more of CT, I have to give up some CT plus 1. Right? I can't have my cake and eat it too. If I want my cake, I can't eat that much of it. If I want to eat a lot of the cake, I can't really have just the cake anymore. Well, I mean, I guess I still have the cake. It's just in me and not in front of me. So if I hold utility constant, I have to give up some of one of the inputs for more of the other. What that implies is the indifference curve is downward sloping everywhere. The slope of any indifference curve is always going to be negative. There is, in fact, a mathematical proof for it, but I am not going to go through that. Right, but let's see. And we'll be addressing it though, a little bit. Okay, so this leads to the next section. My apologies for that weird pause there. And sometimes as you're looking through your notes, in the context of what you're teaching and all that, sometimes you may decide like, hey, I think I want to teach a little bit more of this or a little bit less of that. The utility maximizing point of consumption. Now remember, if you remember from the first homework, right, we had a utility function we had x to the alpha times y to the beta, where our income was defined by the price of good x times the amount of x we consume, plus the price of good y times the amount of y we consume. Now, if you recall from this, right, the marginal rate of substitution was the marginal utility of x over the marginal utility of y. The ratio of the marginal utilities. Right, what was that in this case? Well, the marginal utility of x was alpha times x to the alpha minus 1 times y to the beta. Marginal utility of y was beta times x to the alpha, y to the beta minus 1. And what did this end up coming out to? Well, it ended up coming out to alpha over beta times y over x. All right, but then we also had the derivatives of this guy right here, the price ratio. Price of x over the price of y. Right, well, if we had this in just xy space where you consume good x and good y, right, so I'm sort of helping you visualize what you did in the homework. This price ratio was the slope of the budget line. Right, but a little something extra to it, and it was that it was negative. I won't go through the mathematics on why it's negative, but if we use a method of Lagrange multipliers, we would see that it would be negative. So the slope of that budget line would be this right here. Right, the ratio of the price of x over, or the ratio of the prices of x and y. And if we also remember from intermediate micro, all right, if I were to just plot out this utility x to the alpha times y to the beta at any one particular point, let's just say it's the one here, call it u1 or u prime of xy. This point right here, where they are equal, is the utility maximizing consumption bundle of x and y. It's the point of tangency where I have maximized my utility subject to a budget constraint. Well, this is for micro. This is intermediate micro stuff with indifference curve analysis. But let's look for a second at really how not different this is if we have this stuff in a dynamic framework. Right here, utility is actually in a way easier because it's additively separable. So lifetime utility is the utility of current consumption plus beta times the utility of future consumption. Right, and what was our constraint again? Do we remember what the constraint was? I'll give you a second to try to remember what the constraint was. Seconds up. This was our constraint. All right, if we wanted to rewrite it a little bit differently, well, we had this, so I could move the CT over here, or sorry, CT plus 1. I made a mistake. So I get CT plus 1 equals all this. Well, if I move this 1 plus RT times CT over here, right, I get 1 plus RT times CT plus CT plus 1 equals 1 plus RT YT plus YT plus 1. Right, if I wanted like the discounted present value of this, if I wanted to know what the present value of my lifetime budget constraint is, I would divide everything here by 1 plus R. I would have that. Either way we can do it. You can look at it either way, because it's the same thing. And it's just telling me sort of in what period I want to be looking at this thing. If I want the discounted present value, well, this is what I would use. So that's what I'm using here. So this is my constraint. Like that. So what is, when I'm looking at this thing, the slope of the indifference curve? What's the slope of the indifference curve? Well, if we remember, it's just the marginal rate of substitution between the two. And remember, the slope of the indifference curve is always negative. So the slope of the indifference curve, I'm not going to go through the calculus on this. Is negative u prime of ct divided by beta times u prime of ct plus 1. And if you remember the slope of the budget line, is negative 1 plus r. Right, so this is the price ratio. This is the marginal rate of substitution, the ratio of marginal utilities. Now, if you remember, in the previous graph that I showed you, well, the marginal rate of substitution was equal to the price ratio. So the marginal rate of substitution is equal to the price ratio. I set negative u prime of ct divided by beta times u prime of ct plus 1. So I have marginal utility of current consumption divided by beta times the marginal utility of future consumption. I set that equal to negative 1 plus RT. Well, if negative stuff equals negative stuff, that negative just kind of drops away. Is this looking a little familiar to you? Let's multiply both sides by beta u prime of ct plus 1. U prime of ct equals beta times 1 plus r u prime ct plus 1. I wonder what this is. Let's do an example. Let's say we have log utility. What's the u prime of ct? When we have log utility is 1 over ct. We got log utility, u prime of ct plus 1 is 1 over ct plus 1. Now let's plug that in over here. I get 1 over ct equals beta times 1 plus the interest rate times 1 over ct plus 1. Ooh, that's interesting, isn't it? That's our Euler equation. All right, so if I take the marginal rate of substitution of my utility function, so marginal utility of current consumption divided by marginal utility of future consumption, and I set that equal to the slope of the budget line, which is the price ratio. So the marginal utility of current consumption divided by the marginal utility of future consumption, which was also just u prime ct divided by beta times u prime of ct plus 1. So I set those two equal to each other, I get the Euler equation. So the Euler equation is really an optimality condition that's telling me what the optimal current future consumption bundle is given the interest rate. Right, you can think of the interest rate as like the marginal cost that we face between consuming today or tomorrow. Right? That 1 plus the interest rate is telling me at the margin, if I want a little bit more current consumption, well, I've got to give up future consumption at a rate of 1 plus r. That's kind of cool. So the Euler equation, like I said, is an optimality condition. Let's see what this thing looks like in a graph. So I'll have a graph I've been drawing for a while now. Yeah, it's good enough. Right, I've got this. Now if I want the slope of the budget line, it's this right here. So this is my budget constraint. And if I want the utility function that achieves a point of tangency, right, because remember there's like a lot of different level curves of utility. there are a lot of indifference curves. We want to basically find what indifference curves, remember there's like this whole continuum of these different indifference curves given various levels of income. I want to find the one that exactly touches this budget line at one point and only one point, a point of tangency. So if you remember, when we're taking derivatives, right, it's like we kind of have, we've got this curve, we got like some secant line, which a secant line will go through a curve at 2 points, right? We keep rotating that line more and more and more until eventually the distance between those 2 points on the curve converge to each other, and we have only one point where that line touches the graph, and that is the point of tangency. That's what the derivative gives us. So at the utility maximizing point of consumption, I get something cool. I get my Euler equation. So let's call this CT star. And call that CT plus 1 star. And at this point right here, I don't want to screw up my markers. This point is given by the Euler equation. U prime of CT equals beta plus, or beta times 1 plus R times U prime of CT plus 1. The Euler equation gives me that point. Now what do I need from this Euler equation to be able to get that point? Well, one, I need to know what the utility function is, because just U prime could be literally any utility function. As long as it satisfies the requirements of the utility function, it could be anything. We don't know. So that's not very helpful. So I would need to know what the utility function is. I would need to know what the inputs of consumption are, and I would need to know what beta is, as well as what the interest rate is. If I wanted to know any of that stuff. But at the utility maximizing point of consuming and saving, essentially, yielding a consumption bundle, CT star and CT plus 1 star, well, I can figure that out from the Euler equation. How far into this are we? Exactly 1 hour 14 minutes. Okay, so that will conclude this lecture. The next lecture we'll talk about the role of income in these models, and then we'll talk about what happens if there is a change in the interest rate. All right, meaning there's a change in the slope of the budget constraint. That will be in the next lecture video. So until then, enjoy whatever time you have in between watching this video and the next video.